See, it takes a person who does adaptive optics to give me a good PSN.
So our first speaker is Alycia Weinberger, composition of extrasolar planetesimals.
Yeah.
Okay, thanks. I'm going to pick up right where Ted left off, so that was perfect. I'm going to say, well, we have all these great gas tracers for what's happening to the composition during the early stages of planet formation, but most terrestrial planet formation happens in the later stages of the assembly of planets. Once a lot of the gas is gone and you've either incorporated the bulk materials that you care about into solid bodies, so planetesimals generically means comets or asteroids, or you haven't, right? And the same way that we deduce the history of the solar system from looking at the remnant asteroids and comets, which is what's sort of shown in this combination of cartoon and real data for what we think happened in the formation of the planets in the solar system, we can then actually try to trace the solid material with observations of disks at each of these time periods. So here's TW Hydra. These are the stages that Ted was just talking to you about. But after the gas goes away at about 3 to 10 million years, we're left only with the solids that were able to form during that time. And it's those solids which are coming together to form the terrestrial planets. So what do we have then, and how do they come together, and what is the incidence, for example, of giant collisions that would form things like the moon? Those are the questions that I'm interested in picking up on now, starting from about 10 million years and proceeding for the entire lifetime of a planetary system. You know, we still have a disk of dust created from our planetesimal belts, the asteroid and cometary belts that we see as the zodiacal light. If I have time at the end, which I probably won't, I'll talk about detecting exo-zodies. So these are all real observations of disks, just to make the point that, you know, we're not making stuff up here. Okay, but it's hard to trace solid material, so they don't have those beautiful spectral lines that the gas has that let us know in detail the abundances of individual elements. So we're stuck trying to measure things from the actual reflectivity or emissivity of those solids. And it's a very basic type of information, but in principle, I think with some work, we're gonna be able to determine things like the carbon to oxygen ratio of planetesimals by busting them up into micron-sized dust, the same way that happens as in collisions and evaporations in our solar system, and looking at the composition of those dust particles. Okay, so what we imagine is that two solid bodies come together, they collide, and they produce a whole spectrum of dust, from micron-sized particles all the way up to meter-sized or even sub-kilometer-sized particles. So in the most massive of these collisions, we'd like to know how long does this process take then to clear the dust out? How long do we have to observe it? Does it modify the dust in such a way that we need to understand that modification process in order to understand the composition of those planetesimals that collided? And how often do these collisions happen? And therefore, what are the diverse outcomes that can happen in planetary systems? So that's a lot. I'm not going to cover all of those. I'll just show you an example. This is the dustiest disk that we know around an old star. Actually, it's an old binary system, but in this particular case, we don't think that the fact that this is a binary star system really has anything to do with the dust that we observe around it. So this is the dustiest system. So this is a giga-year-old, at least a giga-year-old star system that had a relatively recent collision that produced so much dust that we infer that the body involved in the collision was probably of order of the size of the 5th largest asteroid in the solar system. And the effect that we see in this particular case is the infrared emission from all of those small dust grains. So here's in the black line, the light you expect from the star, and here is the emission from the small dust grains produced in that collision. And if you like infrared spectroscopy, you'll immediately notice that we see crystalline and amorphous silicates that show that this was a rocky body. What we don't see is any cold bodies in the system, any planetesimals colliding out at 50 AU in a Kuiper belt that could have fed those planetesimals into the inner system. So it's really like we had two asteroids at 1 AU around solar-type stars bust up into a lot of very small dust grains. And now we want to know what is the evolution of that dust? So this is a planet-making process. Well, in this particular case, it may have been a planetesimal busting process, right? But what happens to that dust? If you just calculate how from the number of dust grains and where they are, you say, okay, well, the orbital timescale of those dust grains is about a year, because they're at 1 AU from solar-type stars. It's a little shorter. These are slightly more massive stars, and there are 2 of them. The collision time, just from the number of grains, you expect to be a couple of years. So what happens to the dust grains? They have to be micron sized to producing these peaks. Well, we think they should just get blown out of the system. And so you should see a giant halo of grains. They should be removed. And over time, the flux from this disk should just go down. As you break up the larger pieces, you produce small dust grains. They blow away. You break up some more larger pieces. They produce small, etc. Okay? And in fact, our understanding of those processes is essential to our then trying to figure out how disks evolve. So we went out to actually measure, given that this has pretty short timescales, how did the dust change over, say, a few years where you would expect it to be evolving? The answer is it actually got brighter. So this is in red, the observation that I just showed you. It's now a restricted wavelength range from what I showed you before, but in red it's exactly green, it's exactly the same observation I showed you. So sorry if anyone is red-green colorblind, I did a bad thing here on my color scale. So the bottom plot, which colorblind people should be able to see, is our ground-based observation that we made in 2004 from a combination of ground-based telescopes on Mauna Kea. So let's hope we continue to get to make observations from Mauna Kea like this. In 2006, we made those observations I showed you on the previous slide from the Spitzer Space Telescope, and then in blue, a couple of years ago, we made those, 4 years ago, those observations from Sophia. And the disk has been steadily getting brighter over a very human timescale, which is weird for anything in astronomy, really, for things to happen on year timescales. We actually also have new observations from last fall, which we'll be able to add to this soon, I hope. So this picture we have of just big things breaking down into small things and clearing away the small dust is not entirely correct. And you can interpret this in there are a few different possibilities for what's happening here. The time scale for drawing dust into the star, I didn't point it out on the previous slide, but it's of order tens of thousands of years. So if you can draw in the big things, then you'll make them hotter and you'll make them produce more dust. So that's a possibility. You only have to move these things in by 5% to make the flux go up. So maybe we're seeing this competition of processes between drawing dust in and blowing it out. You could also launch what we call an avalanche, which is that you bust up a bunch of big things, you launch some small grains, and those small grains get blown out by radiation pressure, and then they produce a very efficient secondary cascade of small particles. And so that could be what's happening. But we see so many small particles created in the last 10 years that it's basically like we busted up an all new 50-kilometer sized asteroid in this system. So what we're trying to learn about here are both the physics of how long it takes to clear these types of collisions and how they happen, and also how frequently they happen. So I said I was showing you the dustiest source that we've ever detected, but you can play a counting game. Okay, so we can go out and look at all the stars in this stellar neighborhood and ask how many of them have these really extreme asteroid collisions at late times, and just count them. Okay, and actually there are only a half a dozen or something of these known, so you don't even have to be able to count very high. Now we say, well, okay, that number that we observe, the fraction of all the stars we observe, 100,000 stars that have this hot dust, that is going to be a product of how many impacts per star there are, right, to produce this dust, how long those products last, which is what we're trying to measure in observations like the previous set that I showed you. And you need to factor in the age of the stars because, you're looking at things that have been around from anywhere from hundreds of millions to billions of years. So I played this counting exercise several years ago, and the answer came out to be like a few tenths of a giant impact per star. So you would essentially expect every star, nearly every forming planetary system, to have a late giant impact. So by late, I mean all the gas is gone, you're left only with your remnant planetesimals, and you actually smash a couple of them together to produce a large amount of dust. Now, in principle, we could do this counting exercise much better now, but we're really having trouble getting the systematics of those statistics right. So I want to redo it, but the completeness issue of exactly how many stars we've searched to exactly what limit is a really tricky one when you're using all sky surveys to survey the sky. And so I don't have an updated answer from what I published, I guess in 2011, as this fraction of giant impacts. Okay, so that's the late stages of planet formation, right? That's like the moon forming impact that we were just looking at. The much more common set of impacts that we look at is the impacts of comets with each other in rings of cometary belts around other stars. And this is one of my favorites, so I'm going to use it as my example. It's HR 4796. And this is a very Kuiper belt-like sized ring. It's at 70 astronomical units from its star. The star is more massive than the sun, just to warn you. Okay, and this was an observation, and I'll show you in a minute how we made it. So what you're looking at, though, are the collisions of individual cometary bodies making micron-sized dust grains. And we want to infer the compositions of those dust grains to thereby look at the compositions of the comets. We want to do that again for asteroid belts, and I'll show you in a minute how we think we might be able to do that. Okay, so composition means spectroscopy. But in this case, we're looking at the spectroscopy of cold solids. And they have none of those beautiful, sharp spectral features that you get from cold gas, even. So we're left with what I call poor woman's spectroscopy, which is taking pictures of the disk at a bunch of different wavelengths and putting it together into a spectrum. So this is what we were able to do a few years ago from the Hubble Space Telescope. These are translatable into wavelengths, So this is in the visible 1.7 microns, 1.8 microns, 2.0 microns, and 2.2 microns. If you're a super infrared spectroscopist, you know that there's a big water ice absorption at 2.0 microns, for example. That's why we chose it. Now we can also use emerging technologies on the ground to do this again at both higher spatial resolution and in a wider range of filters, because we build the ground-based instruments and we can put in whatever filter we want. We don't have to rely on what got launched on the Hubble Space Telescope in 1990. So this is the adaptive optics mirror that we use at the Magellan Telescope to correct for the Earth's atmosphere, which is the major obstacle in imaging these faint disks next to very bright stars. I show this because in a couple minutes I'm going to show you simulations for what we think we can do with the next generation of these observational systems. All right, and so with that, we're able to go further into the infrared. Well, 2.2 microns overlaps what I showed you with the Hubble Space Telescope. Here's 3.1, here's 3.3, and 3.7. And we can also do narrowband optical filters, which we can't do with HST. You just get all the optical light at once with the instrument on HST. So we can do a bunch of narrowish band optical filters. Okay, so we can put all of that together into a spectrum. So here it is. Like, I was pretty proud of this spectrum. It took hours and hours of time. Even though I realized you're going to be like, that spectrum has 11 points on it. Okay, so here is the brightness of the disk relative to the star as a function of wavelength, and it has this interesting shape, which rises, it gets brighter as you go to longer wavelengths, that's what we call red, and then it flattens out. Here's that 2.0 micron water, and here's the stronger 3.1 micron water ice absorption band. So much like what Ted just talked about, we don't see convincing evidence for water ice on these presumably cometary-like, but not really cometary-like grains. They look iceless. You can see we did a model in blue here that showed kind of the most amount of ice that you could put on those grains. So we can infer from these models the ratio of solid carbon, which is very absorptive and tends to make your spectrum red, and solid silicates, which hold most of the oxygen, and water, which would hold, of course, even more oxygen. The problem is in the right, which, if I had just showed you this left plot, I'd be like, look, we can really infer the composition of solid planetesimals, but in fact, our models don't do very well at simultaneously predicting the thermal emission of those same grains. And so we know we've got a modeling problem. This is something that we're trying to address currently by making laboratory analogs and taking meteoritic analogs of planetesimal material and measuring their optical properties, and then using modern theory to calculate what those would look like when we illuminate them with starlight of different wavelength regions and temperatures. So that's an ongoing work. But the goal is to be able to infer essentially the carbon to oxygen ratio of the solid material from spectroscopy and the visible to the near infrared. All right, so besides those models, how can we improve on this in the future? So starting in November, there's going to be a new instrument on Magellan, which is called MAG-AO, Magellan Adaptive Optics X, right, for extreme. Okay, so this is being built at the University of Arizona by Jared Males and Larry Close. And we did some simulations for what our favorite disk would look like. There's a hypothesized inner ring that has never been observed with current instrumentation, but which there's a hint of in the thermal emission from the dust grains. And so we said, okay, let's put in an inner ring consistent with the spectral energy distribution and see if we could image it with our new adaptive optics system. And the answer is yes. So you see this inner ring now that's approaching more like you would say an asteroid belt as opposed to a cometary belt, where we might expect that there's a difference in composition between, say, planetesimals in the inner belt and an outer belt if we go on the evidence from our solar system. We can, of course, take the next bigger step, which we really want to do, which is to build the next generation of extremely large ground-based telescopes. And in this case, the simulations we did for the Giant Magellan Telescope, which will be a 25-meter telescope on Carnegie's Last Campanas Mountain in Chile. And here, those previous things I showed you were like duck soup. We're like, well, that's too easy. It doesn't demonstrate what we could really do with this telescope. So we stuck in a really tiny, true asteroid belt at 5 AU and showed this is what that asteroid belt, if you could detect it, would look like with present generation telescopes. It's basically you can't resolve it, but with a 25-meter telescope there you resolve an actual 5 AU true asteroid belt. And then we go through that whole process I showed you before, I hope, of doing the spectroscopy and actually seeing whether we see a compositional difference between the dust in the outer solar system and the dust in the inner solar system in other systems the way we clearly observe it in our solar system. And I'll just finish by saying, how much time do I have actually?
7.
5 minutes. Okay. About the composition, that we do already know that at least some systems have differences in their composition. So those bodies that are out at, say, 100 AU, 70 to 150 AU, sometimes they produce gas and sometimes they don't produce gas when they collide. So this is a paper that Meredith McGregor, who we'll talk later, led, but looking at data we took with ALMA, that Chem Large Millimeter Array. In the red background here, you're seeing our Hubble Space Telescope images made a few years ago of these disks showing these wild wings. Sometimes people refer to these disks as the moths. You know, one hypothesis for these has always been that planets are tossing planetesimals or dust grains out of the system. So we look at the dust, but the other really interesting, so these things look identical essentially in the dust. The scattered light, they're different distances away, so they may look a little bit different to your size, to your eye, but essentially the distribution of dust, both in small grains and in large grains, is identical in these two systems, and yet this one has a ton of carbon monoxide gas relative to the dust, and this one has none to our very best upper limits with ALMA. So we do know that there's diversity in the production of comets, or things that are located at cometary-like distances, planetesimals, amongst stars of different types and different locations. Okay. Okay, so finally, since I do have 3 minutes, I want to just conclude with what do we know about the Exo-Zodiacal Light, the very dust that we do observe in our night sky as sunlight scattered off of small dust grains. So the way you see it here, this is again Las Campanas Observatory. The sun is below the horizon. Dawn has not started yet, but you're seeing the individual dust grains created by the evaporation of comets and the collisions of asteroids in our system, reflecting the light of the sun, which is below the horizon, back to us. All right, so this integrated light is about 1 part in 10 million of the light of the sun. So it is a really tiny signal, yet it is actually probably the second most observable thing about our solar system from the outside, the first being the reflex motion of the sun due to Jupiter orbiting around it. Because, you know, even though that's a tiny signal, It's way bigger than the signal you get from a planet at the same distance, which would be more like 10 to the minus 10 of the reflected light, because it's like you busted up some planets right into a very large surface area. And it's also a detection issue for future Earth-finding missions, because this is the major source of astrophysical noise for detecting Earth-like planets around another star. You have to detect it against the background of whatever dust happens to be there, which may depend on the architecture of your planetary system. So we've had a project for the last decade or more using the Large Binocular Telescope in Arizona to null out the light of the star. So basically, this is the double slit experiment using 2 telescopes. So you use your null, your destructive fringe on the star, and you let the disk come through the constructive fringe of your interferometer. And last year we published our just detection rates. There's an updated paper to this that's in the works, which will hopefully come out later this year. So these show previous surveys looking for how much of this exo-zodiacal dust, that's basically dust at 1 AU, there could be. And you can see our limits are much better. And the bottom line is that we can say that most sun-like stars have less than about 10 times the level of dust that we see in the solar system. And that's not super satisfying, because we are not yet down to the ability to detect 1 exo-zodi, or equivalent of what we have in the solar system around other stars. So you could have up to 13. Depending on the model, you might infer that the typical star is down more like a few. But this is very model dependent. So we don't yet know exactly how much asteroidal dust is in other systems. And this is another project that, like the Giant Magellan Telescope, for example, could improve upon. Okay. So here are my 3 takeaway points. We have the capability, I think, if we understand how to interpret our large surveys, to calculate how many moon-forming-like impacts have happened around other stars and when they happened. And we can study in real time the physics of how you remove the dust from those systems. We will be looking for how many systems have architectures like ours, so they have asteroid belts at 1 to a few AU that are producing dust that can both be a source of signal for the structure of the planetary system and a source of noise for looking for extrasolar planets. And as you saw, I think we have the capability to study the materials, the solid materials that actually were involved in the buildup of terrestrial planets, and understand whether the Earth's composition is typical amongst all the planets that form. Thank you.
We have time for just one question.
It's quick. So, do you have another significant constraint in your models for scattering versus grain size from the polarization measurement?
We do, and so I didn't show the polarization measurements, but essentially what we're doing is we are making dust grains of different shapes and sizes, calculating how they interact with electromagnetic radiation, and that is true for both polarization. There are fewer polarization measurements. It's actually, the other big constraint we have is scattering angle, how much they throw light in the forward direction versus the backward direction, and also what their albedos are as a function of wavelengths. So we calculate all those things and try to interpret them all simultaneously.
That's it for Alycia. Let's thank her again.
This is Russ's pointer.
Next,
Can I leave your pointer, Russ?
No, you can keep that.
Okay. Thank you.
Next we have John Chambers, theoretical models for planet formation.
Thank you. I'm going to talk about, first of all, give you a quick overview of where we think theories for planet formation are today, and then I'm going to look at how we can improve on some of the uncertainties in those models using observations of extrasolar planets. So the starting point, as you probably gathered, for planet formation is a protoplanetary disk. We've seen this image already several times. Many young stars are accompanied by these disk-shaped clouds of gas and dust, which are very roughly similar in size to the solar system. By mass, we think they're aboard a 99% gas and 1% dust, with dust being anywhere from sub-micron size up to millimeter to centimeter. That's as big as we can see, and it goes on up from there. These things only last for a few million years. So here's a plot showing a fraction of stars with disks as a function of stellar age. I believe these numbers are still fairly relevant, and they only last a few million years. And the planar nature of these disks is presumably the reason for why the solar system, planetary system at least, is planar. So the starting point for planet formation is the dust grains. Lab experiments have shown that these very small submicron sized dust grains will readily stick together during collisions, forming these fractal aggregates. These are real experiments. However, as the aggregates get larger, they collide at higher speeds than the gas, and also their surface area to volume ratio goes down, so collisions get less and less efficient at sticking, and eventually reach a point where instead of sticking, these fragments either bounce off one another or they start to break each other apart again. And that leads to the idea that there's probably a maximum size for growth, which is somewhere in the millimeter to centimeter size range, and we call these particles pebbles. And these have already been alluded to also several times. Pebbles are not stationary, they drift, as was mentioned just a few moments ago. The reason for that is that gas, that's the pink stuff in this protoplanetary disk, has a pressure gradient, and to first order the pressure decreases moving away from the star. And that means that molecules of gas have to orbit the star more slowly than they would if they were a solid body, because of the partial pressure support they receive from the pressure gradient. A solid particle like a pebble, however, has to go around the star at a speed dictated by Kepler's law. And that means if you're sitting on the particle, you see a headwind, because the gas is orbiting more slowly, it looks like the gas is coming towards you. And that headwind removes energy and angular momentum from the pebble and causes it to move inwards towards the star or towards the nearest location of high pressure. Here's some calculations of how fast that works as a function of pebble size. For very slow, very small particles, they can only go at terminal velocity, and that is quite small for small particles. And big particles are less affected by gas drag because they're very massive. And in between, there's a spot somewhere in the centimeter to meter size range where particles drift at maximum rates, and those rates can be very high, 1 AU in a few hundred years. The upshot of this is that in the planetary region, the region where planets are forming, there's probably a continual flux of pebble-sized particles, millimeter, centimeter-sized particles, flowing inwards from the outer disk, and this provides a continual supply of material with which to build planets. Planetesimals are often considered the building blocks for planets, and by planetesimal I mean an asteroid-sized object. If you look in the asteroid belt or in other small body populations in the solar system, this is the number versus size, you see there's a discontinuity at a certain size, very roughly 50 or 100 kilometers. You see that in the Kuiper belt, you see that in the irregular satellites of the giant planets which we think are captured. And that modeling suggests is the location of the size at which the primary bodies formed in the solar system. So objects which are bigger than about 50 or 100 kilometers are mostly primordial, we think. Objects which are smaller are caused by the breakup of a few of these big objects to form a cascade of fragments. How do these 100 kilometer plus size bodies form? That is still somewhat uncertain. The best candidate model at the moment is the streaming instability, which is if there is some structure in these disks, and we've already seen that there really is structure, you get temporary maximum pressure locations, particles will tend to drift and pile up at those locations. If you can get enough particles located in a single region of space, the collective gravity of all those particles will cause them to collapse, shrink, form a solid body. And here's a simulation of this in action. This is a 2D slice of a 3D disk. The sun is in this direction, and this material is going around. And this is after just 4 orbital periods. Color code shows the amount of dust located in a particular region. The dust was originally uniformly distributed, and here in a very short space of time, we form these little clumps, and these are gravitationally bound. The simulation stopped at this point, but there's every expectation that these would collapse to form solid bodies. These are the planetesimals. Now, we think that that process that forms planetesimals is pretty inefficient, so there's probably lots of pebbles left over. You see them in disks, as we've already heard. So you've got a few of these planetesimals which can act like seed bodies. We now think that probably one of the main ways in which they grow is by sweeping up the pebbles which are still left over. And it turns out that there's a sweet spot for this process. If you're a large planetesimal which is formed and you encounter other smaller planetesimals, they will only collide with you if their trajectory is just right. If you're a micron or a submicron sized grain, you're very much coupled to the gas, and the gas is likely to blow them right past you. But if you're in the centimeter, millimeter, maybe meter size range, you experience drag, but the drag timescale is comparable to the timescale for you to have an encounter with a planetesimal. And the combination of those two things means that you lose energy on the same timescale that you have an encounter, and that greatly increases the capture probability. So here's a hydrodynamic simulation of this process in action. The 3 different lines show 3 different sizes of particles. You can see some of them go zipping right past, some of them never get there because they're too tightly coupled to the gas, and then at the sweet spot, which is this 0.1 size, everything that comes within this red circle, which is the gravitational capture radius of the planet, essentially the Hill radius, everything that comes within that circle is captured by the planet. And that leads to very rapid growth, at least in some cases. However, all things don't last forever, and this is the case for this process. Once a planet reaches a certain size, it starts to perturb the gas in its vicinity, and it opens up a gap, at least a partial gap in the gas. And you now introduce a new pressure maximum just outside of the orbit of the planet, and instead of the particles zipping on all the way through or hitting the planet, they get stalled at this point outside. And pile up, I think Ted mentioned this a little while ago, and you stop the supply of pebbles to the planet, and the planet stops growing, at least in terms of sweeping up pebbles. This is called the pebble isolation mass, and critically, that mass increases with distance from the star. Close to the star, this isolation happens at very small masses. The mass gets bigger and bigger as you move further away. If you have a big enough planet, you can acquire gas and become a gas giant. All planets bigger than roughly the size of the Moon capture temporary atmospheres of gas when the gas is still around in the protoplanetary disk. But for these low mass planets, there's a balance between gravity pulling inwards and the pressure in the planet's atmosphere, and the situation is stable. But once you exceed a critical mass, which is very roughly a few Earth's masses to 10 Earth masses, this situation can no longer be maintained, and the gravity is always stronger than the pressure gradient, so gas starts to flow inwards onto the solid planet. How fast this occurs depends on how fast the planet can radiate away the energy which is generated by the accretion. While it's still accreting pebbles, you get so much energy input to the system that it's very, very hard to capture gas. But once the pebble supply stops, the only energy being brought in is by the gas itself, and so the gas can start to accrete if you're above the critical mass. And the bigger the combined system gets, the faster more gas comes in, so you get a runaway process. So here's a numerical simulation of that, starting off with a core which is at this critical mass, just a little bit above it. The gas accretes slowly at first, and then faster and faster and faster until they've turned off the simulation, because it's essentially you're running away until something stops you. The other thing that's been alluded to already is the fact that planets don't stay put, they migrate. The reason, well, there's more than one reason, but the main reason that I'm going to worry about here is that if you have a planet, which is located here in this numerical simulation, embedded in a disk of gas, and this gas is color-coded by density, and they truncated the simulation at these 2 points here, that's why these regions are black. You see that the gas is no longer smoothly distributed or uniformly distributed. You get these spiral waves launched from the location of the planet. And gas in these waves is overdense compared to other regions, and that generates torques that pull on the planet and move its orbit. And in general, these torques are not symmetric. Typically, this one is bigger than this one, and that, on average, tends to remove energy from the planet's orbit and cause it to move inwards, and that's called migration. That also depends on the mass of the planet. Okay, so that's the outline for how we think planets form, at least many planets. Alan Boss may talk briefly about another channel for forming subgiant planets. But the model, as I've described it, still has a good deal of uncertainty in it. And I'm going to talk about how we can use observations to constrain some of these uncertainties and improve our models and understanding of how planets form. So here's, you've seen many variations on this plot already. This is data I pulled off the Exoplanet Encyclopedia a couple of years ago, so it's already out of date. Just showing the radial velocity planets, but there's enough to get the picture here. This is mass on this scale and distance on this scale, and you can see even in this plot there's many hundred planets. When you add in the transiting planets, the Kepler planets, that number goes up quite a lot. But these distributions are biased. All the techniques which are used to find planets are biased, some more so than others. And various people have attempted to try and construct de-biased estimates of the real population, the real underlying population. So here are 7 different studies I dug up from the literature a couple of years ago, looking at different slices of phase space, and this again is mass and distance. And each of these regions tried to construct a de-biased estimate of the population in that particular region. So some of them cover regions of wide ranges of masses, and some of them wide ranges of distances. And some of them overlap to some degree, but you get a fairly good coverage of this region of orbital phase space. Some of them are more speculative than others, but I've weighted them all equally in what I'm going to talk about next. So using these de-biased estimates for the population, I actually did a population synthesis approach, and the idea here is to use a simple model for planet formation, which puts in the main ingredients that I've talked about, so pebble accretion, gas accretion, planetary migration, and run it many, many times and try and optimize the uncertainties in the model. So here I tried very hard to reduce the whole uncertainty of planet formation to just 8 different model parameters. Then ran this model millions of times and compared the results with the observations in order to improve the parameters and get a better fit to the data. And because I was running this so many times, I optimized it automatically to try and avoid biases which might be introduced by me doing it just by eye. I used the particle swarm optimization scheme. The idea is that you have particles which represent possible solutions moving around in phase space. And this would actually be an 8-dimensional phase space for the different parameters for the model. And each step in the optimization, they tend to be accelerated towards the best solution which any particle has found so far, and also the best solution that particle has found, with some drag force to stop them spiraling out of the region of interest. There are certainly other ways you could do this. This was just a relatively simple optimization scheme that I put together based on people who've used this for other fields. So here's the best fit case for 2,000 stars, so very roughly about the number of stars we see with extrasolar planets. These are the results from having 1 planet per star, and this is the mass of the final planets, and this is the distance of the final planets. And they're color-coded by the mass of the protoplanetary disk, so I considered a range of protoplanetary disk masses, because as we've heard, there is some uncertainty in this number, although perhaps not quite as much as when I did this study. But you can see that the blue ones, which are the most massive ones, tend to form the most massive planets. That's not a huge surprise. Whereas the low-mass disks tend to have a really hard time forming big planets. These are the gas giants up here, and these are the super-Earths, and these are the Earths. This dashed line here shows you what you would see if you had a 1 meter per second precision using a Doppler radial velocity survey. So anything below this line is basically invisible to the Doppler radial velocity surveys. Kepler would have seen some of these objects, but many of these are too small to observe at all.
John.
Okay, yeah. This is what happens if you look at where the planets form. So this is looking at the final mass as a function of the initial formation location. And this plot actually tells you quite a bit more about what's going on. You see that all the planets that formed inside of a few AU never got big enough to accrete gas. They reached this pebble isolation mass that I talked about earlier and stopped growing, and these would never get beyond the Earth or super-Earth stage. In the outer disk, if you're in a massive disk, objects can reach the pebble isolation mass and they can be big enough to then accrete gas. And then they migrate inwards. So here's some evolutionary tracks showing just a handful of the planets I just showed you on the previous plot. This is distance and this is mass, and each planet moves along one of these tracks. So The vertical lines here are when they're accreting pebbles. They reach the pebble isolation mass, they stop accreting pebbles, and they start accreting gas. They're also migrating inwards. The amount of gas accretion is slow to begin with because they're cooling slowly. As they get bigger, they get this runaway gas accretion and they start moving upwards in this diagram. And because they're migrating as well, you see some of them end up in the inner disk and some of them remain in the outer disk. So the favored values that you get from this optimization scheme is you want large seed planetesimals, Pluto mass preferably. You want the atmospheres to be able to cool rapidly so that they can get to this gas accretion phase. You want the pebble isolation mass to be small, and you don't want migration to be too fast, especially for giant planets. You want migration to slow down as planets get bigger. Otherwise, they all pile up close to the star, which is not what we see. Here are some sample systems. Each row of symbols here shows a different planetary system formed by the optimization scheme for the best case scenario. And this is now looking at systems with 4 planets per star. And they're color-coded by gas content. So the blue ones are what we think of as gas giants. The red ones are what we think of as rocky planets, and the green ones are intermediate. And the symbol size shows the mass of the planet. So you get some systems like this one that look a little bit like our solar system. You also get quite a few which are just small rocky planets, and quite a few where they're in chains of resonances, like these 3 are in resonance chains, these 3 are all in resonance chains. Some of them where you form rocky planets and completely fail to form anything in the outer disk. Finally, I want to talk about solar system analogs. Now, this study was not designed to reproduce the solar system, it was designed to reproduce the observed extrasolar systems, but you do get a few systems that look like our own. So I picked a couple of criteria for what I'm going to call a solar system analog. One is that you need to have at least 2 planets which are bigger than 50 Earth masses, like Jupiter and Saturn. And these want to be outside of 3 AU, which is comfortably inside of where Jupiter and Saturn are. And I said all the planets which are closer than 3 AU should be smaller than 2 Earth masses. Make sure that they really are rocky terrestrial planets. And when you impose these constraints, you get a success rate somewhere in the region of 1 to 4%. 1 to 4% of the stars that I simulated in the best fit scenario have analogs to the solar system according to these fairly liberal criteria. And here are some examples here. I think these are most of the successful cases from one of those simulations. And some of them are not too bad. I particularly like this one because it had Saturn smaller than Jupiter, but you get a range of variation even in the solar system analogs. The analogs have some things in common. One is they all have large disk masses, and as I showed earlier, you need large disk masses to form gas giant planets. They also have large disk radii, and the reason for that is that you want a massive disk, but you don't want to concentrate the gas too much because that increases the migration rate. So you want lots of mass in the pebbles which can drift inwards, but you want the gas to be fairly diffuse, so that means you want to spread the gas out widely. It's a way of having your cake and eating it. And also the giant planets all begin at large distances and then migrate in to some extent. So to summarize, planetary system, characterize the nature of the systems is strongly determined by this pebble isolation mass that I talked about, the point at which you stop growing by accreting pebbles and can in principle start accreting gas. In the inner disk, the planets never reach a big enough size to form, to accrete gas because they reach this pebble isolation mass and stop growing. In the outer disk, if the disk mass is low, again they never reach the pebble isolation mass even because growth is very slow. However, if you have both a massive disk and you have a planet in the outer disk, it can grow fast enough and big enough to reach the pebble isolation mass and then accrete gas and form the gas giant planet. And the combination of that plus having small planets in the inner solar system happens roughly 1 to 4% of the time. Thank you.
Questions for John?
I'm curious if you have an opinion about this idea that has gotten some press lately in the wake of Oumuamua. I think Michelle Bannister wrote a paper that there should be a sufficient population of the right kind of interstellar objects that could actually help to catalyze planet formation by sort of entering it at a time when, the critical time when this pebble formation was going on. Have you seen that paper? Do you have an opinion about it?
I haven't read it, I've heard of it. That's possible, I don't know how realistic the numbers are. That to some extent just pushes the difficulty back one step, and that they must have formed somewhere.
I guess it could affect the time scale if there were sufficient objects, but it wouldn't really change the mechanism of that.
Right, and we think that the Plantesimals must have formed pretty early in our solar system based on their cosmic chemistry.
Thanks.
One more question.
Yeah, so thank you first for showing results of a pretty straightforward, few tunable parameters planet formation model. I was wondering if you go back to the mass versus period or semi-major axis, that one. There's still a gap between 0.1 and 1 AU, where various transiting surveys have found lots and lots of planets. So I was wondering if you had an idea of what physics your simple model is still missing but could benefit from including.
Yeah, so one thing I skipped over is the fact that there's an inner edge to the disks in this model, and that inner edge varies somewhere between this point and this point, depending on the star. And so that's why you've got a pile of things in this region, and this region is less populated. I wouldn't be at all surprised if the migration models would change somewhat in the future and build in this region. Planetary migration is notoriously difficult to understand, and small changes can make a big impact from this kind of model. So that's probably the explanation.
All right, that's all we have time for this talk. Our last talk for this session, and also the last one before coffee break, is Jason Wright, searches for habitable planets.
Did you load it under your login?
Yes.
Okay, so I was asked to talk about the search for habitable planets, but we're also talking about SETI here, and I'd like to prime the discussion for later on. I also had a SETI-related flash talk that didn't make it, and so I added that in. So I'm actually going to start with some discussions about SETI, and the way I'm going to shoehorn that into my talk is by arguing it's a shortcut in the search for not just habitable worlds, but inhabited worlds. So if you just want to jump to the real question, which is not just are we alone, but is there anyone out there we might be able to communicate with? Is there other complex life like ours that is technological? Then SETI, that's the promise of SETI, that we can jump to the end of this whole path. And there were some questions asked earlier by Ken, for instance. What does it mean that we haven't found anything yet in SETI? What are we doing wrong? And do we need new strategies? And my answers to those questions are essentially, it doesn't mean much that we haven't found anything because we haven't looked very much yet, and I'll quantify that in a second. What are we doing wrong? Well, we're not searching very much yet, and that's one thing we're doing wrong. And do we need new strategies? Absolutely, we need new strategies, but not because the old ones have failed, but because we don't know exactly what we're looking for, and we need to keep our minds open to the forms of technology that we might be able to detect. So to quantify this issue, it came up earlier that Jill Tarter liked to say that the amount of searching that had been done was equivalent to going to the ocean and dipping a drinking glass in and looking for evidence of large marine life in that drinking glass. It's unlikely you're going to catch a fish or something in there. That was back in 2010. That was an order of magnitude calculation, and so some students and I went through and tried to quantify more precisely the size of the so-called cosmic haystack with which you would look through for particular kinds of radio signals and do that calculation more rigorously. Also, since then, there were a couple of radio surveys that did a huge amount of work, most especially the Breakthrough Listen survey of nearby stars. And what we came up with was that the drinking glass was now a large hot tub. So we're making progress, And in truth, if you were in the right part of the ocean, then a large hot tub's worth of water, in certain spots, yeah, you might have found a fish. And so, especially if we're targeting the right places, we're not just randomly searching the galaxy, then that large hot tub might actually be, starting to put some real upper limits on things. And indeed, the Breakthrough Listen survey is looking at a much smaller haystack, so to speak, targeting nearby stars, not just random parts in the galaxy. It's important when we do this, we have to, in order to do that calculation, you have to know what searching has been done. And unfortunately, a lot of the searches that have happened have not been published as upper limits, and we have to infer from the fact that we know it happened, they said they did it, we know what instrument they used, we know what the feed was, what the haystack volume was, that they searched for that. And that's something Jill Tarter's been maintaining for a long time, and a student of hers, Andrew Garcia, compiled all of the known searches. Some of my students contributed to some literature search. So you can go to TechnoSearch at the SETI Institute, and you can see all the searching that has been done. And it's not very much, but projects like Breakthrough Listen are dramatically increasing the amount of searching that's been done. To do this, you have to search the literature, and if you're interested in finding a paper, has someone ever thought of X in SETI or something, I encourage you to look at the new ADS interface. It has two features that are fantastic for this. One, you have full text search of every entry. You can search every paper's full text. So if you want to know if a certain concept's in there, you can go do that. The second is that my student Alan Reyes has compiled bibliographies from a lot of people and a lot of places and attempted to find all of the SETI entries in the astrophysics data system. And so this is in proofs right now, this paper. But you can access our bibliography with the keyword bibgroup:SETI. And that will limit your search to papers that are at least tangentially related to the search for extraterrestrial intelligence. So that's a feature that we're offering the community. And we will maintain this, it'll be live. As papers come in, I'll try to keep it up to date. Here's Alan, who put that together, and then Will and Colin, who both contributed to the TechnoSearch. This was the Penn State graduate course in SETI. My excuse for showing this was our visit here to Green Bank, where we conducted observations with Breakthrough Listen. They designed their own radio SETI search and executed it, and we're working on processing that data right now. This is now a formal course at Penn State. And for people who want to know more about the search for extraterrestrial intelligence, we've posted the curriculum. In particular, we essentially read foundational papers. And so if you go to, if you can just Google this, or I'll send you the link if you like, and you can find links to all of the papers that we covered, including foundational papers, but also much more recent papers. And we take a very broad view of SETI, not just radio SETI, but every way we might find technologies. One issue with looking for technologies from habitable planets is that we have to guess what we're looking for. And there are some ideas that are better than others. And so some people really like narrowband radio emission, and some people really like pulse lasers, and some people really like looking for waste heat. Another student in the class, Sophia Sheikh, has put together the 9 axes of merit for such searches, where you consider, well, how hard is it to look for it? So these ones up top are practical. And then, is it a good thing to look for? Like, is it something very brief, like we look for nuclear war on another planet? That would be pretty brief. Or is it something really, really long-lived? Something that might last a very long time, like a Dyson sphere or something like that. An important one on this list is ambiguity. So if you see narrowband radio signals, 1 hertz wide, right, you win. There's no natural source of those. That's definitely technology. It's almost always Earth technology that's stuck in your telescope beam, but it's definitely technology. Whereas if you go looking for something like Dyson spheres, you have a different problem because your upper limits are hard. You see, mid-infrared emission coming from an old star. Sure, that could be a Dyson sphere, but it's much more likely to be about the dusty disks we just heard. And so you have a lot of natural confounders. And so I've put some thought into how you turn those into upper limits. And this is the slide I was going to present. You look at the whole sky, and you sort everything on the strength of the technosignature you're after. So you look at every star that might have inhabited planets, and you say, I'm looking for Dyson spheres, it's waste heat, mid-infrared emission. And you sort all the stars you have. The most extreme star you've got is your upper limit. There are no technosignatures above that. That's a result. You've learned something about the absence of technosignatures, and it's going to be a ridiculously high upper limit, but it's something worth calculating. And then you can go down and look at these objects. First of all, eventually you'll find, okay, that's like a protoplanetary disk or something. Well, those are really interesting. In fact, you have found the most extreme cases of those. So now you've got interesting astrophysical results. And as you say, yep, protoplanetary disk, it's a regular disk, it's an AGB star, your search upper limit drops down to some threshold where you just have so many natural objects, it's hopeless. I like this approach to SETI because when you're doing this and you're doing astrophysics, you're following Freeman-Dyson's first law of SETI investigations, which is that every search for alien civilizations should be planned to give interesting results even when no aliens are discovered. And that's something I really love about so many of the SETI efforts going on, is the constant publication of papers, not just from the things you don't detect, but the things you do with the technology that you are developing. Okay, so so we're trying to do this, we're trying to incorporate this philosophy at Penn State. We have a nascent center. It's not funded yet, but we hope it will be soon, the Penn State Extraterrestrial Intelligence Center, where we'd like to put all of this philosophy together and also create a hub, an academic hub, another academic hub for the search for extraterrestrial intelligence. We'd like to think about new things we can do at Penn State. We have the Astrophysical Multi-Messenger Observatory Network that searches across the electromagnetic spectrum and all four forces of nature. We have a lot of reasons to think, people have suggested that these might be carriers of signatures of technology in the universe, and we are in a good position to work on that sort of thing. We also want to harness the big data revolution. We have a big supercomputer on campus. We think a lot about LSST and how we can leverage the time domain and all of these all-sky surveys to go anomaly hunting, sort things by a technosignature, go anomaly hunting, and then do astrophysics on the cool anomalies that we find. So if you're interested in this philosophy, if you want to know more about it, these dates are tentative, but we are planning on having a symposium at Penn State a little under a year from now. I'll announce this formally when the contract is signed, but that's what we'll be doing, so mark your calendars, especially if you're working on some SETI stuff that you'd like to present at the symposium. Okay, so that's the easy way to find an inhabited planet, in the sense that it's a shortcut. If you win, you've gone all the way to the end of the line of finding an inhabited planet. Another easy way is to just go online and look for a gallery of habitable planets, because there is one, the Habitable Zone Gallery. So if you want to find a planet in the habitable zone, well, we actually know a lot about a lot of those. There's a whole list here with 128. We have 128 known planets that orbit entirely within the habitable zone. Now, we've already heard if you want to be inhabited, we think we need a solid surface, but I'll point out many of these are gas giants which presumably have moons. And so if we think moons are a common byproduct of giant planet formation, then we probably do have solid surfaces here. And so I would say, especially from a SETI perspective, that all of these systems are interesting, and we think that there should be perhaps icy bodies with solid surfaces, or liquid bodies or solid bodies in that region. So I say also easy, it's not just going here. A lot of work went into finding these 128 planets. Most of these are either found by Kepler or are giant planets that were found by the radial velocity method. So that's the harder way. The harder way is to first find the planet, and then next we're going to characterize if it's habitable. So how do we go and we find an exoplanet? Well, there are several methods. I'm going to talk about these 5. There are others, but I think these 5 are the most important to talk about in this context. Fortunately, we're going to hear a lot about most of these in other talks, which left me time to talk about SETI earlier. We've already heard Jessie in her talk about transits, and then we'll hear Angie Wolfgang in their talk about transits next, I think. And then Dolokhov and Jeff Kuhn will both talk about imaging, which is a good way to go finding them, although in a lot of cases it'll be easier to find them via, for instance, radial velocities first, and then follow up with the imaging. Microlensing, I'm not going to talk about and won't hear much about. It's great for populations of planets and finding out how many habitable zone planets of a certain mass there may be. But most of the planets found by that method are not amenable to the sort of follow-up we'd like to do to establish that those planets are actually habitable. We'll hear Alan talk about astrometry later. And so that leaves for me the main one of radial velocities, which is my wheelhouse and where I've done most of my work in this department. And then step 2, once you've found the planet, you want to do some sort of spectroscopy. You want to do something that tells you the characteristics of the planet so that you know that it's in fact a solid surface and maybe it has water on it or something like that. and we'll hear Natasha Batala talk about that later on. So, let's talk about radial velocities. So this was the first method to find an exoplanet. It's not on a loop. What's going on? Sorry, this was supposed to be a loop, but it's not going to loop, so I'm just going to have to show it over and over. Great. It's going around and around and around. And the important part is that when the planet goes around the star also in its own little way goes around the planet, around the common center of mass. And as a result, the spectral lines at the bottom, due to the star, wobble back and forth. The important things to know about the radial velocities are that you can find new planets with them. In fact, for a long time before Kepler, most planet discoveries around other stars were made via this method. And that's because you're almost completely insensitive to the orientation of the orbit. You get the orbital period of the planet, which yields its effective temperature if you know something about the star. So that's really good. You have found planets that may be in the habitable zone. And then the relevant thing is it gives the mass of the planet. Normally it gives the minimum mass of the planet because there's an ambiguity in the inclination. But in cases where you have transits, that ambiguity is lifted and you get the true mass of the planet. So this is good and bad. It's good because it means we have access to mass. It's bad though because it's proportional to the mass, the detection sensitivity. And so if you want to get down to things like Earth mass planets, you're going to run out of sensitivity and it just gets harder. So that's great. That gives us the habitable zone gallery I showed earlier. But if we really want to get to habitability, we need to supplement radial velocities with transits or imaging. Transits are great because they yield the radii. They also tell us get rid of the minimum part of the mass. Radius plus mass gives density. Now we're at bulk composition and we can talk about habitability. The other thing is that a transit implies the atmosphere is going in front of the star. We've already heard from Jesse about how that can yield atmospheric characterization, and that's what we really want to get after. So just to illustrate this point about densities, here's an old plot. It's pretty out of date now, but it illustrates my point, which is that we can get the mass of a planet from the radial velocities. We can get the radius of the planet. This is linear in radius, with Jupiter being about here. And you can get a sense of where the state of the art, at least a couple years ago, was for planetary masses. If something's up around a Jupiter mass or so, then the precisions we're talking about that we need are around 1 meter per second. And so we have pretty good masses on all of these transiting planets. And in fact, it's the radius of most of these planets that weren't well enough known to really nail the density super well. And then you'll notice there's a different class of object down here that we knew even before Kepler, where as you go down in mass, you see now we're starting to talk about upper limits in mass. The radial velocities get below 1 meter per second, and we don't really know what the masses of these are to very high significance, even if we can detect them by transit. And in the Kepler era, we just have gobs and gobs of planets down here that we know are super-Earths or sub-Neptunes or terrestrial planets, but we can't actually measure their masses yet with radial velocities. But we are working on it. Radial velocities are moving forward. We now don't just talk about precise radial velocities, we talk about extremely precise radial velocities. And there was a workshop, the third one, held in State College a while ago. The most recent one was in Grindelwald, Switzerland. This has become a biennial thing. And at the State College workshop, we made a list of all of the precise radial velocity machines coming online. And I was going to make a plot to show in talks that listed them all, but it just turned into tiny font because there's so many of them. There were over 26 new Doppler velocimeters as of 2 years ago, so I'd say maybe 5 of these are commissioned and working now, and a whole bunch more coming. But every major observatory has invested at least something in developing a precise radial spectrograph. And so the goal here is to provide masses and discovery for all of these planets, and many of these instruments are driven with habitable zone planets, terrestrial planets in mind. Now this is going to disappear on us. There are there's sort of two routes here to habitable zones. If you want to find something around the sun, it orbits once a year and it's 10 centimeters a second. There's an advantage to going to lower mass stars because the center of mass is farther, so the swing is larger. And the planets are closer in, which means they're more likely to transit, and they go around more often, and so you get more beats in a year. And so there's a lot of reason you might want to go to lower mass planets when thinking about the habitable zone. Now we've already heard that M dwarfs might not be the greatest targets, maybe they flare. There's been the pendulum in the community on whether M dwarfs are good places to look for habitable planets has swung back and forth a few times. It's another route, but it requires different sorts of technology. And the reason is if you really want to get to a low mass star to exploit this advantage of much larger radial velocities, around 1 meter a second, where we think we can already get, very close-in planets huddled close to the cooler star to stay warm, you have to move into the infrared, because that's where the flux is. For a star like the sun, optical spectrographs are fine. You can use CCDs, which we love and are stable and linear and all of that. But if you really want to go to M4 and later, and when we talk about M dwarfs, they span almost a factor of 10 in mass. This is a huge range of stars. Early M dwarfs you can still do in the visible, and many have been done. Late M dwarfs you really have to work in the infrared. So that means moving to infrared detectors, which are not as great as CCD detectors for this kind of work. But on the other hand, you only have to get to 1 meter a second, and so the tolerances aren't quite so bad. And so both routes are being pursued by the community to look for both kinds of potentially habitable planets around both kinds of stars. So here, Jim showed a version of this we've seen a couple times now, where the x-axis is some sort of indicator of distance or stellar installation or orbital period, and the y-axis is the temperature, or on the main sequence, the mass of the star involved. So for reference, here we have the sun at around 5777 kelvins, right back here. And then we go out and we find out there's Venus and there's Earth, way out here past 100 days. And here's one rendition of the habitable zone, where Earth is right at the inner edge and Venus is way inside the optimistic habitable zone. And then as you go down the main sequence to lower mass stars, the habitable zone comes in. And so if you want to look for potentially habitable planets around M dwarfs, here again we have the shorter periods. And also, as we've seen, we have the higher semi-amplitudes of the velocities of the stars, so they're somewhat easier to find. So the two kinds of instruments are the things that are going to look around up here and the things that are going to look down here to try and cover this whole space for habitable planets. So if we start down here with the M dwarfs, there are a couple instruments. At Penn State, we have commissioned the Habitable Zone Planet Finder. Another important one is Carmini's, which has both an infrared arm and a visible arm. Here we see the visible arm. And so here's an example of two planets with periods of 5 days and 11 days, so really close in, around Teegarden's star, which is only 4 parsecs away. And these are temperate planets. And so this is an example, and if you look, you see a few things. First of all, the amplitude here is just over 1 meter a second on these things. So this is a really small signal. Secondly, you can look at the scatter here because it's the visible arm. And it's a very faint star. And the scatter's up at a few times that. So you need a lot of points. This is really expensive. You have to beat down your instrumental noise to see these signals buried underneath your instrumental noise. And that's one of the big challenges of working here in the infrared, or working down at these masses in general. This is a nice plot that they made of that in that paper. Again, stellar effective temperature, and here, as Jim did, they're plotting the stellar insolation, although they're going the other way from Jim's plot. And we see Teegarden star with two different estimates for the stellar temperature, the two planets compared to the two habitable zones. And then we've seen these names before of terrestrial habitable zone planets, Proxima Centauri, the TRAPPIST system that we heard before, GJ776c. So we're starting to fill this in, and you'll notice it's almost all happening down here, either with Kepler up here or with M-dwarf infrared machines here. We would love to get up closer to more sun-like stars, where the only example of a truly habitable planet we have lives, which means we really need to push towards much lower velocity precisions here around the hotter stars. So we've seen this. Okay, so there are a couple instruments coming online I'm going to talk about briefly that are designed to do this. At Penn State, we're building NUID. NUID is an extremely precise Doppler spectrograph in the optical that will be on the 3.5 meter wind telescope at Kitt Peak. It is a public instrument. So the WIN 3.5 meter is an NOAO telescope, open skies policy. Anyone can propose to use this facility instrument, anyone in the world. And so we are building this for the whole community on this 3.5 meter telescope. The motivation for NASA is to follow up test targets and really get at those terrestrial planets that TESS finds. But it'll be useful for lots and lots of things. And then also on much larger telescopes is Espresso, which is being commissioned right now on the VLT. And so has much more glass available to it to go to much fainter targets and collect many more photons. The number of photons you need here is very large. You need bright stars if you're actually going to just have enough information content in the spectrum of the stars to measure these Doppler shifts at the level we need to find these habitable planets. So getting down to 10 centimeters a second, which is what the Earth shift around, how much the Earth shifts the sun, is a huge technical challenge. So just to give you a sense, we have to do these complex error budgets. Normally when you're making a new instrument or tackling a new dimension, there's some tall tent pole that you just got to get over. And that's where all your technical work is going, is the knocking down that tallest tent pole. But we've been at this in the radial velocity game for decades now. And all the tall tent poles are gone, and all the little trees are gone, and now we're just mowing the grass. Everything matters at 10 centimeters a second. And so we worry about the quality of the scrambling in the fibers. We worry about nonlinearities in the detector and charge transfer inefficiencies. We worry about thermomechanical changes because the spectrograph room can't be exactly the same temperature. We worry about how well we can hold focus on the fiber because the scrambling isn't perfect. We worry about how well we know the velocity of Earth around the very center of the solar system and have to incorporate that. That turns out not to matter. That's solved by the pulsar folks. Thank you very much. But it did take some work for us to translate it all into this. So when you do all that, you say, great, we get down to 10 centimeters a second, we can find the planets. No, sorry, it's still a huge problem, a huge astrophysical challenge. And the reason is that stars aren't stable at that level. The surfaces of stars are bubbling and convecting, you've got granulation, to say nothing of stellar dermatology. You've got star spots and flares, and you've got hot spots, and the whole thing is rotating. And so you're not looking at this nice, narrow emission line. You're looking at a bubbling cauldron, and its velocity is changing all the time. So this is data, solar observations taken with the Solar Telescope, which feeds the HARPS North spectrograph. And they do this during the day, and the sun is the one we know best, right? We know the right answer. We know exactly how fast the sun is moving away from the HARPS North Solar Telescope. So this is the ultimate standard star. And they did this in kilometers a second for some reason, but just move everything over by 3. That's 2 meters a second, 2 meters a second, 2 meters a second. That's 1 meter a second. The Earth around the sun, which is, they removed it from here, but it would be buried in here if they hadn't, is a 1/10 of 2 ticks, so it's a 5th 1 tick, and it's annual. It's way buried in all of the stellar jitter, we call it, from the star itself. So I'm confident that the problem now is not a technical challenge. I mean, that's still a huge challenge, but I think the technical game has gotten way ahead of the astrophysics game. So you have to play a lot of, they're not games, we have to work very hard to understand this noise, find proxies for it, reduce it as much as we can in software, and then think about things statistically and take huge numbers of data, huge amounts of data to beat this noise down if we're going to find those terrestrial planets. So my big 3 messages from this talk, because we have got lots of other people to talk about the other ways to find terrestrial planets, but in terms of precise radial velocities, M-dwarf planets in the habitable zone are detectable now, and I mean terrestrial planets. And in fact, we were already starting to populate the diagram. Sun-like stars will require us to tackle this problem. And we don't know how long this will take. We have a lot of tools we're going to use. Our new instruments are going to measure the jitter extremely well. And we have the sun as a touchstone. It's the one star where when the velocity jumps, we can just go look at the sun and say, oh, it was that sunspot there. Now I know how to measure that. And then finally, if we actually want to find a habitable planet, it's more than just RVs, but RVs are an essential complement to transits and imaging, both because they give us masses, they find them, and because they find them in the first place, so you don't have to waste time hunting them. You can just go and see what they are to find that that thing is really a habitable planet. Thank you.
Yeah, Jason, hopefully we'll get a talk from Natasha Battaglia on the last day about transit spectroscopy from JWST. The last time I talked, she's my former student, the last time I talked to her, she was quite pessimistic about getting spectra of Earth-like planets, transit spectra of Earth-like planets around M-stars. Didn't seem to work for a TRAPPIST system, and maybe TESS will find something better, but so that's why I plug direct imaging.
Yes, I also remember Natasha's PhD and remember being very pessimistic about whether Webb was the instrument that would finally deliver us things that said that is a planet like Earth with oceans. And so that's one reason that I lean on imaging as well.
You said that in the case of the sun, we can just look at the sun and see there's a sunspot and conclude where the velocity change is. But the truth is, we actually can't do that because there's a correlation between brightness and velocity, radial velocity on the surface of the sun that isn't very well mapped. And so the largest noise that comes into the radial velocity measurements of sun as a star observations is something that isn't associated just with the occurrence of sunspots.
Oh, I agree. Sunspots for quiet stars are not the dominant. I use that because it's an easy example. Granulation is the dominant source, but there's also variations in convective blue shift from magnetic regions on the surface. So there's a lot, but
It's a really hard problem.
It is hard, but with the sun, we do have Dopplergrams. We do know the Doppler shift of every little piece of the sun, contemporaneous with our observations. And when we integrate up the Dopplergrams, they better add up to what we're observing.
That doesn't really help because you don't have those observations of other stars. So somehow your proxy determination rests.
Look, we can't solve this for other stars astrophysically unless we know the underlying model. And we have this amazing opportunity to have the right answer in everything we could ever want about those stars. If we can't solve it on the sun, I don't know how we're going to solve it on another star.
Here.
Okay.
Could you go back to the sun's image there? So when you say solve it on the sun, do you mean get those blue model the variations in the blue lines so that they are on the order of what you said?
There's a few things. So when a true center of mass motion of a star is a pure Doppler shift, the spectrum of the star, if it's moving, delta lambda over lambda, everything shifts by exactly the same amount. If you change the balance of convective blue shift on the surface because a magnetic plage region came into view, that is not a pure Doppler shift. Certain lines will react differently. You'll see differences in the line shapes. You'll see chromatic effects. It'll look different in the near infrared and the optical. So there are a lot of features in the spectrum, and these are exquisite high-resolution spectra, that should track these. And indeed, if you correlate these residuals with things like the average bisector of this set of lines, or the mean line width in this region of the spectrum, you can start to see correlations.
You see, already if you do a power spectrum on this, you can see some power at a particular...
Absolutely. Yeah. I mean, for instance, you can see the 11-year activity cycle of alpha sin A and B very clearly. And so that's just the balance of magnetic activity affecting convective blue shift. You see the rotational signal. You see spots coming and going at different latitudes. This is similar to the problem of the technical challenge. For active stars, there's a big old spot, it's rotating really fast, that dominates your signal. With here, you're seeing just about everything the sun does at once at a very similar level. It's a hard problem. It's really daunting. And this is where all of our next effort has to be. Now we have the instruments to measure it. Now we've really got to solve it.
And the blank spaces where it was clouded?
I could not tell you why. I might have been like a telescope shutdown. I'm not sure. I haven't read this. This paper just came out recently. I haven't digested it completely.
Other questions before coffee break? Anything? Well, let's just, Jason, thank you very much.